Welcome back. My name is Jayakumar Radhakrishnan. I work in the School of Technology and Computer Science here. So, so before we start our session, I wanted to thank the family of Professor R. Narasimhan, who used to be a professor at this institute until 1990. His family gave us an endowment which supports, among other things, this workshop this time, and also a postdoctoral fellowship in our department, and also some travel support for researchers who are visiting. Professor Narasimhan started in the institute in 1954. He built India's first digital computer at TIFR. We've hurriedly put up a little poster outside which gives more information about Professor Narasimhan's contributions. And also in the journal Current Science, he wrote an autobiographical essay, and we have some copies of that essay here. So if some of you would like to take a look. So our speaker today for the Professor R. Narasimhan Memorial Lecture is Sidharth Jaggi from Hong Kong, and he'll be speaking on recent advances in covert communication.
Many thanks for the invitation and for organizing all of this. I know none of this is easy ever. I was especially reminded of this when I was reading Men, Machines and Ideas, an autobiographical essay by Professor Narasimhan. There's a few copies that they printed and put over here. And you know, Professor Narasimhan says, well, the combination of the contribution one is able to make in any field is a function of three independent variables: time, place, and effort. But you have to be at the right place at the right time. Effort alone isn't enough, and I've been lucky enough to be at the right time in the right place. But being at that time in that place in India meant, for example, they built one of the first computers here in India, but the challenge, one of the bottlenecks in actually commissioning it was just a room with suitable air conditioning, and that took 2 years to set up, right? So yeah, just doing these things is challenging, and it's somewhat inspiring reading this. The breadth of his contributions, just getting a system up and running, is entirely non-trivial. Anyway, I just want to spend a few words about that, and I would encourage you to read the thing if you get a chance. So let me begin my. Yeah, so I'd also like to acknowledge the people on whose shoulders this work was done. So in particular, my student Howard Pakhoche, who's graduated since with his PhD, my current student Eric Zhang, Eric Xiaosheng Zhang, and my constant collaborator Mayank Bakshi. He'll in the market. He's currently a research faculty in Hong Kong, but he's hoping to come back to India soon. So this will be, of course, a biased personal opinion on covert communication. And after defining the problem, I'll just talk about. I'll try to give some sense of. In the first part, I'll try to give some sense of the development of covert communication over the last 10 years. What sorts of things do we know, and so on. And some of you have heard me give versions of this talk before. The latter two parts, I'll talk about some newer work, recent code constructions, or at least analysis, and also robust covert communication if someone's trying to jam you as well. Okay, so roughly 3 parts. That's what we have to look to. So the basic model is one where Alice wants to. So Alice is maybe, let's just for the purposes of this thing, say that she's in prison. She wants to talk to Bob, a cellmate or someone. But and she can either talk or she could be silent. And if she's silent, then she is not saying anything. And we'll pretend that in this case, the input to her channel is all zeros. If she's saying something, then she says something. Unfortunately, there's a warden, James the warden, or Billy the warden, and if he figures out that Alice is saying something, then there'll be a penalty for Alice. He'll come and punish her or something, withhold her privileges, maybe give her rotten food, right? So there are consequences for being detected. So you want to be covert. So really, like, in a real world setting, what would you do? You would whisper, right? So really, this problem is, one way of describing it is, it's the problem of sort of whispering capacity. And notice it's different from the usual version of information-theoretic secure communication, where the model involves trying to ensure that James the warden cannot figure out what Alice is saying, right? That's the usual context, like making sure that James doesn't know what Alice is saying. She's saying something, but he doesn't know what. Right now, we'll be focused on the problem of James should not even have a reasonable guess as to whether Alice is saying something or not. Okay, that's a basic difference. Okay, so let's jump into the actual model a little bit in a little bit more detail. So again, Alice has a transmission status, either a 0 or a 1. So she's either silent or speaking. Note there's no probability distribution over this. She may be speaking, she may not be speaking. A priori, nobody has any prior distribution over what the probability of her speaking or not speaking is. Okay, so this should be distribution free. If she is speaking, then she has a message which is uniformly distributed over some set, right? And then if she's silent, then for the purposes of this talk, I'll mostly focus on binary input, binary output channels. So just for clarity, though much has been done since then, you can extend it to fairly general channels. Right now, I'll focus on binary input, binary output channels. So if Alice is silent, then her channel input is the all zeros vector. So she just is silent, right? It's the all zeros vector. If her transmission status is 1, she can use any encoding scheme she wishes. So it could be a code book, it could be something, right? And the output of this is xn. It's an n-length binary vector. Now it goes through a binary symmetric channel. Again, we're focusing on BSCs just for this talk, and then Bob gets a version of this, a noisy version of this transmission, has to decode, and hopefully his probability of decoding is very small, right? So this is just a classical communication problem, nothing really new or novel over here. So what's different? What's new? Well, over here, James has a detector or a decoder or something. So based on his noisy observations of the same xn, so it's kind of going through a broadcast channel, and based on his noisy observations of this xn, which again for the purposes of this talk we'll focus on a BSEQ, he's trying to only detect whether the transmission status is 0 or 1. So is T0, is T1, doesn't really care about the message, but primarily is the transmission status 0 or 1. And if so, then we'll say it's covert. Okay. Now, what's a metric over here? How do we decide if James is doing a good job or a bad job? So we'll say that James's best estimator. So we'll measure this quantity over here, the probability that t hat equal to 1 given t equal to 0, and the probability that t hat equal to 0 given t equal to 1 with appropriate randomnesses. Again, there's no probability distribution over t itself. So this is basically the probability of false alarm plus misdetection, right? So regardless of what the probability distribution over t is, you want to take the sums of these two probabilities. You could also generalize this. You could take a weighted sum or something like that, right? But just for now, let's focus on the probability of false alarm plus misdetection. This should be close to 1. It should be epsilon close to 1. And notice that you can show with relatively little effort that that's equivalent to requiring that the variational distance between two different distributions, and I'll shortly talk about these two different distributions, should be small, should be epsilon small. What are these two different distributions? These two different distributions, one of them corresponds to, so I'm going to call it P0 of Zn. So this is the distribution over the n-length binary sequences that James would observe if Alice was silent, if her input distribution was 0. And as you can imagine, this is a smooth distribution. That's sort of a binomial type distribution. The P1 Zn is the distribution that James would observe if Alice was actually talking. And this, as you can imagine, is much more complex. It depends on the structure of Alice's encoder, right? So maybe there's some complicated codebook here, and that would sort of make it a lumpy distribution. Again, keep in mind that over here, I'm drawing it sort of as a single letter distribution, but really it's an n letter distribution. It's, there are 2 to the n atoms over here. You have to look at the variational distance between these 2 things. And it's not too hard to convince yourself just with a little bit of basic probability theory that this quantity over here, the probability of missed alarm plus false detection, missed detection plus false alarm is equal to the variational distance between these 2 distributions. Okay, so you really want these 2 quantities to look very similar to each other. Okay. So that's hidden within here. So the averaging is over the messages and over the noise that is instantiated to James. Plus any other additional randomness that the decoder may choose to use. You still looking concerned?
No, so P0 and P1
yes.
are what James sees.
Yeah.
They are over.
Yes. So it's only over the Zn sequences. From James's perspective, the prior distribution on the message is uniform, and therefore, or it could be non-uniform, but right now let's focus on uniform. So based on this, he has a prior estimate of some P1 and some P0. He's going to estimate, and as you may imagine, it's kind of like a Neyman-Pearson test. That's the optimal estimator, and you can do something. So you can also phrase it as a hypothesis testing problem, and indeed people have looked at it in this sense. Okay. All right. So that's a basic problem. We want to make sure that this is a small quantity. Other people have also looked at the KL divergence between P0 and P1, which also makes sense in a different context. And there are parallel results in this literature. I'm not going to focus on this too much more, but basically, as long as you have a reasonable metric between 2 different probability distributions, you want to make this metric kind of small for James, but simultaneously be able to ensure decodability at Alice. Okay. What is, I'm sorry? Oh, V. Oh, V here is the variational distance. It's the L1 distance between these 2 distributions. This is the basic model slides. If there are any questions, this really is an appropriate place to ask questions. Good question. You could have different epsilons. Over here, as you can imagine, you can get an exponentially decaying probability of error, right? So here you can really make this much smaller than here. Here, for strong reasons, you can't make this epsilon substantially smaller than a polynomial, and in particular, you can't make it smaller than 1 over square root of n in reasonable settings. Okay. So no, in general, these could be quite different. They have different behaviors. Just for the ease of clarity, I've presented them in the same way. For clarity of it. Any other questions? Yes. Great question. That's the next slide. So, so the rate, as we normally think of it, cannot be positive, as you're possibly beginning to suspect, but something like a rate is, something non-trivial is possible. Decaying. So it won't be, again, exponential, but it'll be exponential and square root of n. So you'll notice that over here, I was careful not to write it as 2 to the nr. It won't be 2 to the nr. It'll be 2 to the square root of n times r. There'll be square root of n over here, and so on. And there are reasons for that, which we'll describe in the next slide. Okay. Good. Yeah. So that was a little Easter egg hidden there. I was waiting for someone to get to that question, which leads naturally to not quite the next slide. But yeah, I've already said this. So it's basically the relationship between the variational distance and the metric we're using over here is described here. Now, so just to give some context, so prior work over here, okay. So first of all, let's focus on this. So it turns out that the optimal throughput for this problem, the number of bits, the number of message bits that Alice can communicate to Bob in such a setting, can never scale larger than square root of n over n channel users. So the rate actually goes to 0. But what is potentially interesting is that you can actually get to square root of n, right? So that term will indeed be possible. So we'll call this quantity the throughput. So instead of scaling by n, we'll scale it by square root of n, and we'll worry about that first order term in front of the square root of n. But that's just the fundamental limit of this problem, and I'll try to describe why that's the appropriate scaling, okay, shortly. That's one thing. So these different works have looked at different metrics, variational distance, scale divergence. Prior work has often, not always, some of our prior work didn't need this, but often has focused on a randomized setting. So when Alice and Bob share common randomness. And notice in this first work, this is really quite nice work by Bash, Gerkel, and Towsley, where instead of BSCs, they had AWGNs and so on. But one potentially major weakness of their work was that to get anything non-trivial, they needed a pretty large shared key between Alice and Bob. Indeed, the shared key was larger than the amount of communication they were able to instantiate from Alice to Bob. Right? That's in any reasonable setting. That's not sustainable. You can't really hope for. You can't do it too often. So one of our first contributions was you don't need this. Block has results. Actually, this is misleading. They basically characterize what is the key required in some settings. You don't need keys. In some settings, you do need keys, and indeed. Okay. So again, we'll get into it in a little bit more detail. But these are some of the references which are useful to look at. Okay. And since then, like since the work of Bash, Gerkel, and Towsley, there's been actually a bunch of work, and there'll be some references to it. Okay. So let's get some intuition as to where the square root of n is coming from. So again, if t is 0, then let's just look at, instead of the n letter distribution, let's collapse the distribution down, and let's just look at the distribution corresponding to the weight of Zn. Okay. And again, this is not really the distribution we are interested in, because we are interested in the variational distance between the probability distribution over Zn. But for now, let's just look at the weight distribution of Zn. So as you can imagine, if Alice is not saying anything, it will be a binomial distribution centered at nq with plus minus square root of n deviation, right? And it will be pretty tightly concentrated. So if you deviate more than order square root of n, then the probability mass will shrink out. Now, when t is 1, then let's pretend that just a single code word is transmitted. What's the impact of that? Well, then the distribution shifts, right? Because you're transmitting a single code word. Now, the mean will then be the single code word plus n times q minus correction factor. So basically, the mean, the expected mean of the observed Zn will be potentially noticeably larger than nq, right? And then there'll be some sort of binomial correction around that. So that's what one would expect, and this deviation around it would still be order square root of n. So if you want to be covert, you really want to ensure that the means, like this mean and this mean, are close to each other, are within the standard deviation of the noise. Only in this case can you hope for these two distributions to be close, even in the case of a single code word. And then you can average it out over many code words. But basically, like one way of proving the converse, which I won't dive into, but this is really this is the key insight. It's not even that deep. It basically just says that if you have too many code words which are too heavy, and what does too heavy mean? More than order square root of n, then the shift becomes noticeable. Then even for any single code word, the variational distance is kind of large. So even when you average over all the code words, this variational distance is large. And then you can easily just use James can easily just use a weight detector. He can just say, if the weight of my observed sequence is nq plus some delta, that delta will typically be like square root of n. If it's larger than nq plus some constant times square root of n, then I'll just say that Alice is transmitting. Otherwise, I'll say Alice is not transmitting. Okay. So this restricts you to code words of weight, of Hamming weight square root of n. Now, once you have a restriction on the Hamming weight of code words, then plug this into your usual information-theoretic converses, right? So it's like a very, very input constrained input to the channel, and a restriction on the weight leads naturally to a restriction on the rate of the code word, or rather the throughput of the code words, and that gives you a square root of n. Okay. All right. So and to get the constants right, it does take some non-trivial work, and I should point to the work of Wang and Warnell, who really got the constants right, and so on. So there's all of that. Again, I should also mention, while I'm focusing on the binary input binary output case, partly because of my own preferences, partly because this audience has computer science people in it, but the first work was in the AWGN context, where potentially this model is more natural, right? Like whispering. So you have a sequence of real numbers being transmitted, and so on. So wherever I said weight, you should think of like L2 norms instead. And again, you can do these calculations, and many of these things are basically similar. So, okay, how was the first achievability proven? Well, they were somewhat similar. So, similar to the usual ideas in in Shannon theory, you just take code words. So now that you know what your restriction on your code is, so just generate random codes with that restriction. So choose code words where where ones are chosen in your code words, but only row behaves like something like order square 1 over square root of n. The constant here actually matters. I'm hiding it. For the purposes of this talk, I'll mostly hide the constant factors just to make the exposition a little bit clearer. So you generate code words like that, and then you generate 2 to the square root of n code words. Again, the constant here matters. That corresponds to the throughput. Again, I'm masking that just for the ease of whatever. And then there are you can do a reliability analysis via standard techniques, which I really won't get into. It is a little bit more delicate because now your code words are very low weight, so you have to be careful in how you define typical sets and so on. But with due care, then things are not too unexpected. So I won't get into it. Okay. All right. So yeah, you can get a probability of error that decays as rho minus order square root of n. Okay, now one way I like to think about describing this problem, I happen to think it gives some level of insight, is via diagrams like this. So again, we're actually dealing with an n-letter distribution. There are 2 to the n objects of interest and so on. It's hard to depict visually. So one dimension isn't enough. So let's try to use sort of 2 dimensions just as a proxy for the fact that this is a complicated object. So on this x-axis here, it's the Hamming weight of the sequences that James will observe. On the y-axis, it's the logarithm of the number of sequences. Okay. So as you can imagine, like the number of sequences of Hamming weight 0, there's just 1, so that logarithm is 1, is 0, here it's 0. But in the middle, it behaves like the entropy function, right? It's log of n choose np and so on. So this is just a visual depiction of all possible binary sequences, but arranged like sort of lexicographically according to weight. Okay. So as you can imagine, like if Alice transmits the all 0 code word over here, which is to say she's silent, then there's a probability distribution corresponding to. So if you just look at the weight, that distribution is like a binomial distribution. And this shading over here is supposed to represent the probability of observing a particular sequence with a given weight. And the shade is darker the closer you are to it, but there are just many fewer sequences, so therefore the average is smaller, right? So okay, we all sort of know this. We've probably even used figures like this in information theory classes that we've taught, right? Yeah, and this is sort of the innocent distribution. This is the distribution when Alice is not transmitting anything. The distribution analysis indeed transmitting something is considerably more complex, right? So let's say you've chosen to use a code book with mean something like some constant times square root of n. Then each of these possible code words will throw out a probability mass, right? So corresponding to each of these code words, there will be a probability mass of possible y sequences that you'll observe, and you'll be taking an average of these quantities. And what you want to understand is the behavior with respect to this complicated average quantity. That's more complex. So this is the active distribution, that's what we call it. And we want to figure out the difference between the innocent and the active distribution. And for a given code, this can be challenging. So yeah, and the metaphor, again, just, like physical metaphor, the physical metaphor I like to think about is these code words are somehow water sprinklers. They're all sprinkling probability mass onto the set of all possible sequences onto the grass. The grass is all possible sequences. What you want to ensure is that the amount of water you get anywhere in your garden is sort of close to uniform, right? You would like to distribute your water sprinklers nicely. I don't know if it helps you. It helps me. So, okay. So we do sort of the standard Shannon trick, which is we don't know how to analyze the properties of any single codebook. So we take an ensemble of codebooks with the right distribution. Each of these codebooks have been chosen by choosing bits with probability order 1 over square root of n, average over them, and then we get this sort of blue distribution. This blue distribution is the ensemble average of all of your codebooks, and then the idea is this ensemble average active distribution is quite useful. You can use this as a step in trying to prove drive your proofs. And I'll try to give at least one proof, or proof sketch at least, based on this ensemble average distribution. Okay. So the trick is, well, instead of focusing on the variational distance between the innocent distribution and the active distribution, just use the triangle inequality. First, take the variational distance between the innocent distribution and the ensemble average distribution, and then try to concentrate the probability that this variational distance, the variational distance between a specific codebook drawn according to the ensemble average distribution and the ensemble average distribution deviates too much. Okay, so concentration is easier to do. This first term, it's sort of the bias, but this bias can be made to be small. You can bound it pretty easily because, relatively easily, because both of these are smooth distributions. This is a binomial distribution. This one turns out to be just a shifted version of binomial distribution, and that we're just trying to compute the variational distance between two relatively well-behaved quantities. So a bit of algebra is needed. It's not entirely like one line, but it's doable. And the second one, well, you have to do some concentration inequalities. There are different approaches. There's some beautiful work by Matthew Block and co-authors where they go via resolvability, via channel resolvability. They look at which is this work by, among others, Han and Verdew and so on, where they look at the output statistics of a channel if the input is a codebook, which really is what we have over here. So channel resolvability in a very extreme regime, and Block et al. Go via that technique. We prefer to do sort of a more hands-on, get your hands dirty approach. We try to actually do this concentration, ab initio from first principles, and in doing so, we get some stronger tools, which will be useful in the sequel when I talk about adversarial jamming attacks and things like that. Okay. All right. So yeah, that first term you can just bound via Pinsker's inequality. You get a loose bound this way. You do have to work harder if you want to get a tight bound, but at least as a first, if factor then Pinsker's is good enough. And then to bound this, use concentration inequalities, which is what I'll focus on. So think of it this way. So let's say you observe a particular Z sequence. So James is observing a particular Z sequence. So which possible code words could have caused it? Like you're standing in the garden somewhere, water is falling on you. You want to figure out which are the particular sprinklers responsible for dumping water on you, right? That's what you're focused on. So let's classify the code words according to type classes, according to conditions. So these are, roughly speaking, not exactly actually, but roughly speaking, these are conditional type classes arranged according to the distances of the water sprinklers from you, or the Hamming distance between the X and the observed Z. Again, the actual difference is not just the Hamming distance of X and Z, but also the Hamming weight of X. So it's basically a conditional type class of X given the observed type class of Z. Okay, but anyway, we decompose all possible code words according to the conditional type classes of X given Z. And we focus only on those on the typical conditional type classes, only on those code words which have reasonable, which are in a conditional type class which have a reasonable probability of dumping water on you. Okay. And now note that the probability of observed Zn, the probability of water falling on you, is just the probability of Xn. So the probability that a particular sprinkler was activated times the probability of Zn given Xn. So the probability that water from that sprinkler traveled to you, right? And summed up over all possible code words. And you do this type class decomposition. So you may as well just focus on the typical type classes. Again, you have to worry about the lower order terms, but you may as well just focus on the typical type classes. And this then basically says, so notice for a particular type class, like once you've fixed a particular type class, well, P of Xn is just constant. The probability that a particular code word is activated is just 1 over the number of code words, right? So that's just 1 over the number of code words. This is always a constant. P of Zn given Xn is constant for a particular conditional type class of X given Z. So once you fix out the Hamming distance or Hamming weight of X's, then this is constant. So really what it comes down to is the number of code words in a particular conditional type class, right? And if the expected number of code words in a conditional type class is large, if there's a large expected number of code words at a particular distance from you, large number of sprinklers at a particular distance from you, then concentration is easy to do. So then the probability that the number of code words, the actual number of code words, is not within the expected number of code words times 1 plus minus epsilon is very small. It's like 2 to the minus omega. Okay. And that's really what drives the analysis. You do have to worry about, atypical events, all that jazz. But really what it comes down to is proving that the actual number is close to the expected number. Why? Because, so this analysis was for a particular code, but you can do the same calculation for the expected number of codes as well. Yeah, so you can just average over the ensemble average. And then the difference, so then the difference between, P0 of Zn and P1 of Zn, I maybe should have put in an intermediate slide over here. Basically, the only difference between P0 of Zn, P0 of Zn and EC P1 of Zn. So the, I'm messing this up. P1 of Zn and EC P1 of Zn. So the only difference between the distribution when Alice is using a specific codebook and when Alice is using an ensemble average codebook is the averaging over the codebook. So it's the averaging of this quantity. It's the averaging of the number of code words over the ensemble average distribution. Let me just say that again because it's a little bit important. The only difference between P1 of Zn, the active distribution, and the ensemble average active distribution at that point is both of them have the same expression, except over here in P1, it's the actual number of code words in a particular conditional type class. In EC P1, it's the expectation over the ensemble average of this quantity. Okay, and if you've already done this concentration over here, then basically you have pointwise convergence. For every observed Zn, these two distributions are very close to each other, and therefore you can just sum up and you get your concentration. Okay, so this part I'm going to skip over a little bit in the interest of time. So this part is basically for the particular binary case. It helps to draw diagrams like this. So this is maybe your X sequence. It has weight something like n times f of x. This is your observed Z sequence. It has a certain weight. This is the number of locations where the overlap is a certain amount, and so on. And you can do combinatorics, and you can figure out what is the expected number of code words in a particular conditional type class. It behaves, it turns out, as the overall number of code words in your code book times something which is a empirical mutual information plus a scale divergence, and so on. So these are relatively standard calculations. This scale divergence term turns out to be negligible. The dominant term, it turns out to be this empirical mutual information. And since your code words are very low weight, since the Hamming weight of your xn's is like order square root of n, so really this empirical mutual information behaves like a specific constant times square root of n, and therefore this constant, it turns out to be the throughput that you can support. So really, it really is just a mutual information, as one would expect, right? It's a mutual information, but with a very stringent input constraint. The input distribution has to be order 1 over square root of n. Okay. All right. So the contribution due to the atypical type classes has to be done. There's a slightly different way of doing it. So use Holmes's dictum. So instead of this, which is the actual quote, you do, well, once you've eliminated all that's probable, whatever remains, however improbable, is negligible. So what you instead do, instead of doing the atypicality analysis directly, which for some reason we find challenging, so instead you prove that the contribution to the probability mass of P1 of Zn, the typical sequence is already at least 1 minus epsilon. So therefore, any contribution to the variational distance from the atypical sequences must be negligible because you already accounted for most of the probability mass via the typical sequences. Okay, that's what I mean by this sort of corrupted. Must be the negligible. I'm sorry. No, it's not must be the truth. Okay, sorry. It was late when I was doing this. Okay, so I believe I have like 25 minutes or thereabouts. Okay. So that first part was, let's call it the classical results in covert communication, even though they're all relatively recent, all in the last 7-8 years. So, but these were among the first few types of techniques outlined in covert communication. And now I'll focus on some of the more recent results in our from our group. Okay, so the achievable scheme I focused on, or just mentioned briefly actually, was random coding, right? You choose codes according to the right distribution, very low weight distributions, and then you communicate. It's not very satisfying for all the obvious reasons. The computational complexity is very high, encoding, decoding. It's hard to say really what's going on. I mean, aside from everything that we know from Shannon theory, it's not satisfying to people who like code. So, computationally efficient codes. And as to sort of mirror the development in Shannon theory, like the first quote unquote computationally efficient codes were concatenated codes. Now, upfront, I admit that even in Shannon theory, the concatenated coding philosophy gives you codes which in principle are polynomial time encodable and decodable, but nobody uses them for pretty good reasons. The rate of approach to capacity is very, very slow. It's like 1 over square root of log n and so on. So take it with a pinch of salt. And the same things are true here, indeed, even more so. So that nobody would really want to use these codes for doing covert communication, but at least as a proof of concept to show that in principle computationally efficient codes are possible here. Well, it's the first step, right? So we'll do the same thing here. We'll do random inner codes and read solver and output codes. I should highlight, okay, so they'll be reliable, they'll be covert, and they'll also be computationally efficient. I should highlight a couple of challenges over here. Okay, we'll get there later. But okay, again, to drive home the point that you really don't want to be using these codes, again, I'm sort of dissing my own work. Okay, so maybe it's more trustworthy because I am dissing my own work. But really, so for example, don't worry too much about this thing here. It's some parameter space. And in some parts of this parameter space, the complexity of our algorithms is like n to the alpha. It's like n to the 22, n to the 16, and so on, right? So not great, right? In principle, polynomial time, and in fact, even to get such performance, the block length is very high. It's like 2 to the n to the something, right? So it's not great. Okay, all right. So having dissed it, now let's go on and try to understand it anyway. Okay, so we'll use the concatenated encoding strategy, and because there are some students in the audience, very quickly just to describe that philosophy. The philosophy is you take your message, which has some NR message bits, break it up into chunks, each with only a small number of bits, only log n bits, some constant times log n bits. Use outer code, use let's say a read-Solomon code, or you could use other codes as well, but use an outer code to add redundancy to your message. And so now you have more chunks, each of the same size, and then use a random inner code to blow up each of these chunks into these blue things, each of length log n. So now you've made each chunk a little bit larger by introducing redundancy into them. I'm sorry? C is less than 1, indeed. In fact, it will be 1 minus so for the BSC, it will be 1 minus the h of p. In general, it will be the capacity of the channel that you're trying to do, right? You can do this for any coding scheme. Okay, so what's the advantage? And then when you, so you want to choose, so the block length you want to choose to be long enough so that random codes works, so that you get some benefit. So random coding for the inner codes, these give you at least some reasonable probability of error. Or probability of success, and short enough so that just brute force encoding and decoding of these inner codes work. Okay? So then this way you'll end up with hopefully the benefits of both approaches, at least to some extent. Because the decoding complexity for each of these chunks will then be will be exponential in the chunk length, which is so exponential logarithmic. So in particular, if this chunk length is exactly log n, this will be 2 to the log n, which is n, right? So each of brute force decoding, each of these is like linear in n, and then there are sort of n chunks, so then it's like quadratic, right, roughly. And then you have to do some read-Solomon decoding and so on. Also, since the probability of error of each of these chunks, since the probability of error in each of these chunks is exponentially decaying in the block length, so the probability of error in each of these chunks is like 2 to the minus some constant times log n, so it's therefore decaying polynomially in n. So therefore, it will turn out that, while a few chunks may have been decoded in error, there won't be too many, so your outer read-Solomon code can clean them up, right? So again, that's the philosophy of concatenated coding. That's what we'll aim to follow over here. And once you start thinking about the parameters of what you want, it turns out that the right way of doing it, like Okay, so you still want sort of message chunks of length log n. But now your code word chunks, you want to be larger. Why? Well, remember, overall in n bits, you can only have order square root of n ones in your actual code word, right? So if you want something like log n bits in each chunk over here, then you want therefore each chunk to be square root of n log n roughly, so that the weight, the Hamming weight within each chunk is something like log n. So each chunk length is like square root of n log n, and these are the types of inner codes you will use over here. Okay, and again your decoding complexity will be low, and hopefully your error probability will be low. Okay, now so the probability of error, so with some analysis, and it's not terribly surprising. It is intricate because you're really pushing Stirling to, I don't know, worry about the second order, third order terms in some cases and so on. So you really have to do analysis carefully over here. So the inner chunk probability of error decays is order 1 over log n, and you can use Reed-Solomon auto, you can get the probability of error down to 2 to the minus square root of n. So that's okay. The major challenge to covertness, and the problem there is, well, firstly, again, the calculations are quite delicate. Again, Stirling's approximation and so on. You really have to crank it out and do a bunch. But really, the problem is, once you're using a Reed-Solomon code, this outer code has introduced correlations, right? You did it deliberately. You did it because you wanted to do this sort of divide and conquer approach, make sure that your inner codes are short enough, you can do some decoding, but some of the inner codes will be incorrectly decoded. You need something to clean it up. So you deliberately introduce correlations in the outer code. So that's useful for Bob, but maybe this leaks some information to James or to the estimator, right? So this is the major challenge that you have to worry about when you're analyzing these concatenated codes. That's why even though these are disworthy codes, they're not really practical, but at least they highlight some of the challenges that specific other code ensembles will face when you're trying to when you try to use them. So so one example of the correlation leakage, so just to look at a very extreme example which you won't use, but a very extreme example would be, suppose you used a repetition code as an outer code. That is, every chunk is just repeated. So each chunk is sending this code as your inner code. Okay, so each chunk is a very low weight code word, right? There's just a single one in the first location, zeros everywhere else. It's a very low weight code word. So a priori, it's not a terrible code, a priori, but a little bit of thought shows actually it is a pretty bad code, because what could James do? So well, I didn't mention it explicitly, I should have, but James does in principle know the code book. So he knows that if Alice is transmitting, she's using a code book like this. So in particular, he knows, aha, the first bit carries a lot of information. I can just focus on the first bit over here, do a majority decoding. If the Hamming weight of the observed sequences I'm getting is very high, then very likely Alice is transmitting something, right? And that's because over here our code book is has introduced too much correlation across chunks. So this isn't a great code. Okay.
Exactly one, right?
What's exactly one?
One of the small chunks, the first one is exactly one.
Is exactly one.
It's too much correlation.
It's too much correlation. Again, extreme example just to highlight the issues over here. Of course, James is observing a noisy version of this, but the noise is still not going to mask that much correlation. Okay. Okay. So here's a second example which begins to show a little bit about why there may be some hope even via this approach for coding, which is okay. So let's say there's these are the three chunks, and here the outer code is A, here it's B. So this is some symbol of 2 bits. So it's like some symbol over F2 square. This is some symbol over F2 square. This A plus B is the sum of those 2 symbols over F2 square. Okay, and then you have the corresponding binary code words corresponding to these things. So what does James get to see corresponding to the first code word? So he's seeing some average of these 4 sort of water sprinkler things. Over here he's seeing the average of these 4 water sprinkler things, and so on, something like this, right? Now, okay, so maybe these 2 parts are somehow the systematic parts. Here you used a random code, here you used a random code, they're sort of uncorrelated. So these don't really leak information either individually or jointly if you used a random code, so that's okay. What you're worried about is this third part, right? So do the first 2 leak any information about the third part? That's the worry over here. And you could say, well, okay, James sees some sequence corresponding to this first chunk, and maybe the plausible things are over here. They correspond to these two code words here. Corresponding to this chunk, they correspond to these two code words over here. So how about for this third chunk? So maybe the set of plausible combinations is reduced somewhat, right? Because information from the first two, he knows that if it's a particular A1, A2 over here and a particular B1, B2 over here, then the corresponding thing must have been something here. So you can try to use that information to filter out what's happening in the third chunk, right? Okay. So this tells us really what sorts of properties we want if we want to still be covert even with the coding, with the outer code, which is, so you want it to be the case that if you observe a particular, if James observes a particular sequence in a particular chunk over here, the expected number of code words over here, the inner code, maybe it has some, this is just an example, n to the 5, n to the 3, doesn't really matter, but there's some polynomial number of code words in the inner code in that chunk, because remember there are log n bits in the inner chunk, right? So some constant times log n bits in the inner chunk. So therefore the number of code words is n to that constant. So maybe there are n to the 5. And from, oh, I'm sorry, the name changed, but James, Willie, whoever, like basically anyone who's not Alice Bob is James over here, okay, is the bad guy. So, so over here, the number of possible plausible code words is n cubed, okay. So you want there to be a polynomial number of possibilities, and in particular, yes, and in particular, Bob will get a much smaller plausible set over here. Right? So you'd want there to be a smaller plausible set, hopefully with high probability close to 1. Okay? So you want this property, you want the property that from James's point of view, there's still a polynomial number of plausible code words. From Bob's point of view, you want the number of plausible code words for most balls to be 1 or close to 1. Okay? So you can use a reliability coding the outer set. Okay, some techniques over here, which maybe I'll skip over. It just helps to, have an oracle who reveals information, a little bit of information, just to smooth up things, so you don't have to worry about it. Don't worry too much about it. But basically, in terms of analyzing covertness, so what happens is, again, from James's point of view, this is these red things are plausible, these red things are plausible, these red things are plausible. So now what you want is maybe that if you look at any specific triplet of potential code words that are plausible over here, then they'll give a particular code word here in this chunk. If you look at any specific thing here, it'll give something here, and so on. So on average, you can compute the expected number. You can compute the expected number of possible combinations that would contribute to a certain plausible code word over here. Okay. So it basically just corresponds to like n cubed to the power of the number of systematic chunks, to the number of chunks where the coding was done independently, divided by, like in this specific parity chunk, divided by the overall number of code words in this parity chunk. So in expectation, there's really a lot of confusion, right? In expectation, there are many different ways in which the messages corresponding to the systematic chunks, which were truly independent, could have combined to give a message corresponding to a code word, to any code word in the systematic chunk. In expectation works out. Concentration is a little bit more, takes a little bit more effort. The first few things you try, Chernoff doesn't work, even McDermott's, at least we couldn't get it to work. And these are mostly just technical issues, just to do with the fact that the expectations of these quantities are somewhat large, the deviation that you want is somewhat small, and so on. So these are in the extreme regime. But luckily, even just a standard, we really should have tried this first, but a second movement method ends up working, and we're okay. All right, so then you do a union bound, blah, 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 and so on. Okay, so maybe just a high level message to take away from this is, just to repeat really, is use a concatenated coding scheme, again, just as a proof of concept that something non-trivial can be done, and luckily it can. The challenge here is that, well, in coding theory, we look for structures which are easily decodable, and these structures which are easily decodable naturally lend themselves to sort of a divide and conquer approach. Okay, try this part here first, then this part, then look for correlations, sort of jump around a little bit. But if your decoding method works in this manner, then those sorts of correlations are potentially exploitable by the estimator as well. So it really does require very delicate analysis to ensure covertness is still possible even via this family. Okay, And you can imagine that it would be even more challenging via, like, let's say you wanted to use LDPC codes and trying to prove covertness for those things, or recently Matthew Block and his co-authors have been looking at polar codes. It's plausible, like empirically it looks like, yeah, these should be covert, but proving it is damn hard because the correlations introduced will be non-trivial. Okay, if I stretch it, I have 8 minutes. I'll try to keep it to 7 just so that there's 1 minute to whatever. But one last thing that we just submitted to stock a few months ago was coding against active adversaries. So the model here is, okay, there's still James over here, he's the warden, but now, you know, he's truly malicious. So you're afraid of him. If he figures out you're talking, if he figures out Alice is talking, he'll punish her. Even if he doesn't know, even if he can't quite be sure whether Alice is talking or not, he might just, to make life hard for Alice and Bob, introduce some noise into the channel, actively try to jam the distribution. Okay, and he knows Alice's potential encoding scheme, so he could really do quite some damage, right? So what can you hope for over here? Now reliability becomes an issue. Covertness is actually now straightforward. If you use the same sort of ensemble of codes, then covertness is okay. It's just a random code. It'll still be covert from James. But can James defeat such a covert code by adding, like, actively adding noise? Okay. So now here's one immediate challenge that presents itself. So let's say this is your code book. Maybe it's covert, so the average weight is pretty low. It's order square root of n. What can James do? He can just choose some other code words, add them to the channel. Again, he doesn't necessarily know what Alice is transmitting, but he can certainly always pretend to be Alice. He can choose some other code words that Alice could have been transmitting, add them to the channel, right? And since these code words are so low weight, in fact, he can add order square root of n code words to the channel. So Bob would then get a superposition of up to square root of n different code words, and really it's all symmetric from his point of view. He has no idea what's being transmitted. So his probability of failure is quite high. The probability that he successfully decodes actually is order 1 over square root of n, right? There are square root of n candidates. His probability of successful decoding is order 1 over square root of n. So at least in the standard plain vanilla model, there's no hope of communication when James is actively active. So why am I talking about this? Well, okay, so it's not possible. So as always, my professor of mathematics and linear algebra used to say, okay, here's how you do research. You draw a target on the whiteboard, shoot an arrow, try to shoot arrows at it, you miss. So then you just erase that target and you draw a target around wherever it lands, right? So we changed the problem. Actually, P.D. Joshi in IIT Bombay, is he still around?
No, he's retired. I met him 3 years ago at station.
Okay. Well, that's a pity. It would have been nice to see him. But anyway, so we redraw the target, right?
He seems quite gentle now.
He was scary. Linear algebra first semester, yeah, it was quite something.
He came on to 1/3 of the class.
Oh yeah. Okay. Anyway, so the probability of decoding is quite small, but okay, so if you change the target and you give yourself a small amount of common randomness, log of square root of n bits of common randomness, then it may be decodable. Okay. Why? Because, well, as those of you who read the tutorial, the sort of a black box way of doing it. And that's what we'll give ourselves. So notice log of square root of n, that's like half log n bits. So if you're getting through square root of n bits of throughput, then okay, log n bits of common randomness isn't so bad, and that's what we'll try to hold ourselves to. Okay, and it turns out to be plausible. It turns out to be possible actually. So that's what in the next 2 or 3 minutes I'll try to sort of describe. But before doing that, yeah, so it's known sort of in standard settings that log n is plausible. I won't talk about the hash scheme. The other challenge you have to worry about is okay, so 2 challenges. One thing to highlight is the usual technique for using the common randomness to disambiguate is Alice first list decodes, Bob first list decodes, and then uses the common randomness to disambiguate from that. But the problem with using common randomness to disambiguate, using that approach is, if you look at this code book from the worst case perspective, list decoding is really a worst case notion, right? It says that regardless of which sequence is observed by Bob, there should not be too many other plausible code words in its neighborhood. That's the notion of list decoding. But since the code words here are so low weight, so suppose James got to see exactly what was being transmitted, he has enough budget to entirely cancel it out. Bob would get the all zero code word. So in this case, if James was indeed able to cancel it out, the number of code, the size of the list must be large. It must be actually the whole code book, right? Worst case notion of list decoding is too stringent. And it is not a problem because James does not get to see actually the whole transmission noiseless. He only gets to see a noisy version of the transmission, right? So it helps to define a notion of myopic list decoding. And again, for those of you who were there in the talk on Thursday, you got to see a little bit of a flavor of what that is. It basically takes into account that James is getting to see a noisy version of this thing. So he only knows that the potential X's that were transmitted were typical, and you need to focus on the fact that, okay, a specific jamming pattern won't corrupt too many of them, okay? The last idea I'll sort of finish on without yet actually talking about the achievabilities. I'll only focus on the converses, the bottlenecks, and then I'll say, well, magically things work out. The other thing is, well, James can still do the following. So he gets to see a noisy version of the transmission. He still doesn't know whether Alice is transmitting or not, but he does get to see something that is correlated with what's being transmitted. So he can add noise that's correlated with this transmission. So for instance, he could do the following. He could choose to, and maybe this is visually a little bit easier to describe. Let me just show you. Okay, never mind. Let me use this graph. So he could choose to act like a certain asymmetric binary symmetric channel. What's really happening over here is that in this channel, he's only going to flip bits corresponding to those bits which are 1 in his observation. Okay, so he's getting to see a sequence of zeros and ones. The ones in the sequence he observes are likelier to have been ones in Alice's transmission. So he'll only choose to flip those bits randomly. Okay. Now this is a memoryless jamming strategy. It's an asymmetric memoryless jamming strategy, but it turns out if you do some optimization, this is actually the best jamming strategy among the class of memoryless jamming strategies. This is actually his best jamming strategy. Okay. Then a significant amount of more work goes into showing that, okay, actually, not only against memoryless jamming strategies, but even against jamming strategies with memory, since James is myopic, he's getting to see a noisy transmission. This is really the best he can do, because any attack vector he chooses, you can get myopic list decoding, then you can use log n bits of common randomness to decode. I'm sort of hand waving over here, but it really does work out. And what he can show is that basically there's a upper bound on the capacity. This corresponds to a jamming strategy corresponding to this asymmetric noise added, and it's achievable via this myopic list decoding plus common randomness. Okay, and then with a larger amount of common randomness, you can also there's a whole bunch of computations. Again, in this case, it does help to dive into the calculations, look at the nitty-gritties, not just focus on the resolvability type approaches, but I don't know how to do these calculations via resolvability, but once you look at the actual calculations for binary symmetric channels, other DMCs, you can do it. There's a whole bunch of stuff here. Never mind all of these nice pretty figures that my student Eric Zhang drew. This is, just look at the music of the slides and and okay, so let's get to the punchline. So what's known for random noise, like if the noise from Alice to Bob was entirely random, then as long as P is larger, as long as Q is larger than P, as long as James has a noisier channel than Alice, then covert communication is possible, and it's a certain mutual information. Here there is actually a penalty if you have an adversary. Covert communication is only possible above this red line over here, and the rates are smaller. And then there's a finer result you can do based on how much, if you have like a larger amount of common randomness, more covert communication is possible, blah, 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 but I won't get into that. Okay, that's it.
There is something like a budget for James.
Yeah. Right. So just to be concrete, you want to compare it to the model where the main channel was just random noise. So if the main channel was random noise, let's say it's a BSCP. So now you compare it with the adversarial channel where the adversary can flip PN bits, right? So that's an apples to apples type of comparison. and even in this setting, the adversary can do some damage. Okay, in the AWGN setting, it's as if and you can try to do similar analysis for power constraint adversary. So if the adversary had a power budget, what could he hope to do? Good. Sure.